Functions are some of the most powerful tools in all of programming, in part because functions help us break our code up into manageable pieces. And the more code we write, the more we're going to want to use functions, so that we don't end up with gigantically long strings of commands. But in order to use functions as widely and fully as possible, for instance, if we want to pass a list into a function, we'll want to make sure that we understand how data is handled within a function. There are several tricky but important details that can have a huge effect on how functions interact with the rest of your code. Most of the difficulties that can arise with functions have to do with the parameters and the variables within the function. Remember, parameters are the main way that we get information into the function. They're the things we specify inside parentheses. Parameters are the values that get passed in from the function call, while parameters are seen from within the function itself as variables. So, we're going to spend some time going through the details of how functions really handle parameters and data. Along the way, we'll also learn about the key ideas of when a parameter or variable is in scope, how to work with data types that are mutable, and what it means for parameters to have default values. Some of these topics that we'll be discussing here are often seen as some of the most challenging parts of programming to grasp. As you gain experience with programming, this will become more familiar and easier to deal with. But it's often a challenge at first. When we say a variable is in scope, it means that at that point in the program, it's defined and usable. I'm sure you know two people who have the same first name. Have you ever found yourself in a situation where there's been some confusion because of that? You have to say, "Oh, I don't mean your brother Joe, I'm talking about Joe from work." Normally, it'll be clear from the situation you're in which Joe you're referring to. But sometimes it can get confusing. Well, the same thing can happen to us with functions. Scope is what helps us keep straight what we're referring to when we use a name. Now, scope is an important way that we make use of abstraction. The bigger our programs, the more important scope becomes. Remember that functions help us conceptually simplify our task. When we're defining a function, we don't have to worry about how all that stuff outside is working. We just know that we can have some stuff coming in as parameters, and we can end up returning something. But the stuff in the middle is just there for our function. It isn't meant to affect all that stuff outside. Scope helps us keep stuff where it belongs. Now, there are two sides every time that we want to make use of a function. The function definition, where our code describes what the function will do, and the function call, where a function is used. Here's a simple function that returns the maximum of two values. Python already includes a function named max that does exactly this. It takes in two values and returns the one that is larger. But let's write our own max function, since that will provide a good way to illustrate the tricky aspects of functions that are hidden from view in the preloaded functions. A function is defined by the header and the body. The header starts with the keyword def, followed by the function name, followed by a list of parameters in parentheses and a colon. Then we indent the body, and we can exit the body by returning some value. When we run our program, the computer comes along and it sees the function definition. It doesn't actually do anything with it at that point other than remember, oh, here's a function with this name and these parameters. And then later on, if that function is called, it's going to remember that definition and use it. Second, we have what's called the main program. All of our code together is called our program, but we'll call the main program the stuff that actually gets executed first, that isn't part of a function definition. As our program gets processed, the first line that actually gets executed is a line from the main program. To understand how functions are really working, let's open the black box and look at how memory is getting handled. Again, the computer skips over the function at first, just remembering that it was previously defined, and executes the first line of the main program. The line a equals 1 creates a variable named a and assigns it the value 1. And then b equals 2 creates the variable b and assigns it 2. Now, in the next line, we have a function call. And here's where it gets interesting. We call the function max, and we pass in two parameters, a and b. When we call the function, there's a whole new area of memory set aside for that function to work in. This is called the function activation record. In that area of memory, we'll first have variables created for the parameters. In this case, we have val1 and val2 variables created in the function activation record. As far as that area of memory is concerned, these variables are named according to the parameters in the function, not according to the names they originally had. These parameters inside the function are sometimes named the local parameters to distinguish them from the parameters on the caller's side, that is, the ones that are listed in the main program. So, when that line, c equals maxdemo AB, is called, the values of the parameters on the caller's side are copied into new memory locations, the local parameters. In this case, the value of A, which is 1, is copied into val1, and the value of B, which is 2, is copied into val2. The function then runs in its own little memory area, and when something is finally returned, that's sent back out to the main program memory area. After that, the memory for that function is all freed up. The activation record is destroyed, leaving that memory free to use again in the future. And our program goes on to the next line of code from the main part of the program. It's important to understand how that memory works, since it's going to play a big role in understanding how parameters and variables are dealt with in a function. Let's look first of all at how names of variables are handled in a function. Here's another simple function named test_score. The function computes a test score as a percentage, given the number of correct answers and the total number of questions. We've got our function named test_score, and it takes in two parameters, the number correct and the total number. Let's say everyone did well on a pretest, and so I'm giving everyone extra credit on the test for 5 questions. So, the function first adds 5 to the number of correct answers. Then it divides by the total and returns that answer multiplied by 100. Remember what we just saw about how memory is handled? From the main program, we have variables a and b. And then, when the function call is reached, we get a function activation record, where we have the parameter values copied into the parameters. So, a is copied into the local variable numCorrect, and b is copied into the local variable total. Now, what happens when we get to this next line, where the value of numCorrect is increased by 5? The variable numCorrect in the function activation record is increased by 5. So in this case it becomes 17. Notice that we do not change the value of the variable a. The value of a was copied into numCorrect's memory location. And when we change numCorrect, we're changing only the new memory location. As far as the computer is concerned, it no longer cares that numCorrect got its value from a. That value could have come from anywhere. It's now just numCorrect. And so, whatever happens there doesn't affect the input parameters. Okay, the next line of code in the function creates a new variable, temp value, that gets the ratio of numCorrect and total. This is a brand new variable, so it has memory set aside for it. Now, this is important. The memory that is set aside within the function activation record. We create a variable named temp value there, and we assign the value to that variable. Finally, we return a value back to the main program. We first compute a new value by multiplying temp value by 100 in the function itself. This calculation doesn't get assigned to any variable, so it's just sitting temporarily in some unnamed memory. Then that value gets passed back to the main program as the result of the function. In this case, the value is 85, so we assign 85 to the variable c. And then, since we're all done with the function call, the function activation record is destroyed. We go on to the next line of code. So, what should happen if we tried to pull in one of the values from the function? Say we tried to access numCorrect, one of the parameters from the function call. Or maybe we tried to access the temp value variable. Well, neither of these are allowed. Look at the memory diagram. There's no more function activation record. All that memory was freed up. There's no way to get those values even if we wanted to. As far as the main part of the program is concerned, those things inside the function never existed. The main program has no way of using them. In this case, the function parameters, numCorrect and total, have a scope of just the function itself. And the variable temp value has a scope from the point it's defined until the end of that function. We would say that any of these, numCorrect, total, or temp value, are out of scope in the main program. Now, scope is an important concept in understanding how functions work. Okay, let's look at how this can get a little bit trickier. This is the same function we were just dealing with. Notice what I'm about to change. I've changed the name of the variable inside the function from temp value to a. What do you think happens here, specifically to the value of a in the main program? Does it change? Let's walk through the code and make sure that we're following it all. We go through the first few lines just like before. We create variables a and b and assign values to them. We call the function, temporarily creating a function activation record, and we copy the parameter values from the call in the main program into the local parameters. We increase the value of one of these local parameters by 5. And now we get to our next line, the one where we're assigning a value to a. Let me explain what happens first and then tell you why it's so important. When we come to this line, we're trying to assign to a variable that hasn't been created in the function activation record. So, we'll create a new variable, a, within the function activation record. And that's the variable that gets the new value. Notice that the original variable a in the main program remains untouched. We have a new variable that's defined within the function. And when we hit the next line, where we compute with a, we use the value of a from the function that we're in, not the value from the calling program. When the function call ends, and the function activation record is destroyed, we still have the exact same situation as we did the first time we ran this program. Basically, it didn't make any difference that the variable inside the function was named a instead of temp value. Now, the reason why this is critically important is that it helps us abstract away parts of the program and focus our attention. We can write the function without worrying about whether the variables we use inside are somehow going to bother the stuff outside. If we've got a large program, we can't remember every instance of every variable that we might have created everywhere else in the program. To keep ourselves sane, we need to be able to consider only tiny chunks of code at a time. So, let's look at a couple more places that scope plays a role. Let's go back to our program that we've had before, where we use the term temp value in the test score function. We're going to make one change. Instead of increasing the value of numCorrect by 5, we'll increase its value by a. What do you think happens in this case? Okay, let's look at the memory here. We get to the function call just like before. Now, when we get to this next line, notice that we're referring to this variable a. We don't have a defined within the function activation record. So in this case, we actually go back to the most recently defined version of a, which is in the main routine. So numCorrect gets increased by 12, so that it has the value 24. Notice that the variable a was still in scope inside the function for reading. But if we tried to assign something to a, like we saw earlier, we'd be creating a whole new variable. Now, this is not really a good way to write code. When you look at the code for this function all by itself, it's not possible to really figure out what it's doing. You don't know what a is or where it came from. The function doesn't stand on its own. Remember that the whole reason we write functions, the whole reason we use abstraction, is to reduce the conceptual complexity. Well, here we haven't really reduced complexity that much, since we still have something outside the function that affects it, and it's not contained in our parameter list. The right way to approach this problem would be to pass a in as a parameter. And it would be even better to choose a name other than a. Now, sometimes you really do need to access something outside the function. Maybe you want to modify a variable in the main program, for instance. You couldn't pass that in as a parameter since it would just copy the value. You couldn't just use the name of that variable since it would create a new local copy in the function activation record. So, how can you actually modify something that's not passed in as a parameter? The solution is something called global variables. First, from what we've learned, what would the following code print? It would print 0. The variable fuel level inside of the function would create a new local variable called fuel level. So, when the initialize function sets fuel level to 100, it doesn't affect fuel level in the main program. But if we really wanted a routine that did this, that initialized the fuel level to some particular value, wouldn't it be nice to have a function that would let us do that? Well, we can do this by declaring fuel level to be a global variable within the function. When we declare a global variable in the function, it means that within that function, when we refer to that variable, we're referring to the exact same variable as in the main program. So, in the code you see here, when we set the value of fuel level to 100, we actually do change its value in the main program. Now, using global declarations is generally discouraged. When you use globals like this, you end up with a function that's affecting things outside it, but there's nothing obvious in the call that tells you that it's doing so. However, there are times, like when you want to initialize values, or you want to read in data and set up variables, that using global variables is very useful, and it can actually aid in abstraction. Now, languages differ in how scope works and the way that parameters are passed. In Python, when we call a function, we make a copy of the values from the main function. Then, when we change the local parameters, there's no change to the values in the calling function. Well, this lack of effect on the calling function is usually referred to as pass by value. It means that we only transmit the value of a parameter when we make the function call. In other languages, such as C++, there's also something called pass by reference. And pass by reference means that the local parameter is exactly the same as the calling parameter. Not just the same value, but the actual same memory location. So, if we change the local parameter in that case, we do get a different effect on the global parameter. In Python, we always pass by value, although there are some ways to affect the parameters outside. Global variables, like we just saw, are one way. Another way to get an effect that seems a whole lot like pass by reference is to use what's called mutable variables. Mutable variables, which I'll explain now, bring us to the surprising fact that there are times that we can modify the value on the calling side through a function. We can consider variables as being one of two types, mutable or immutable. As you might guess, a mutable variable roughly means that the variable is changeable when passed as a parameter, and an immutable one is one that can't change when passed as a parameter. Most of our basic variable types are immutable. If we have an int or a float or a string, that's going to be immutable. That means that when we pass it as a function parameter, the original value can't change. We just copy the value into the new memory location that's part of the function activation record. The immutable value stays the same on the calling side, and that's what we've seen in our examples so far. However, there are also mutable data types, and one mutable data type we've already seen is a list. Because lists are mutable, when we pass them as a parameter, the value in the list can actually change. Let's see how this works. First, imagine we have a function, adder, that takes two parameters and adds the second one to the first one. It doesn't even return a value. It just takes the first parameter and adds on the second one. Then it's done. So, what will be printed here? Well, the integers don't change when we call the function. So, printing num1 still gives 3. Remember that we make a copy of the values when we call the function, and those are what's used in the function itself. If we used floats, we'd get the same results. And the same thing if we used strings. Notice that in all those cases, nothing changes to the parameters on the calling side. They're immutable data types. Now, let's see what happens if we try a mutable value instead. We'll pass in as parameters a couple of lists. What will happen? In this case, the mutable variable means that we can actually change the value within the function. So, in this case, the end result is that the list has actually changed. Our list went from just 1, 2 to 1, 2, 3, 4. In a practical sense, we mainly need to understand whether the things we're working with are mutable or immutable. If it's immutable, it means the function can't change it. But if it's mutable, the function can actually change the value. Ints, floats, and strings are immutable, and lists are mutable. As we learn about more types of data, we'll have to understand if they're mutable or immutable. The objects that we'll introduce later on are mutable, for instance. And if we ever pass something mutable to a function as a parameter, we need to be aware that it might change. We can't assume that the parameters that we pass in will remain unchanged by a function call unless they're immutable. Okay, so let me explain a bit more about how all of this is actually working. I did say that Python was passing by value, so how could we actually change something? When we have something mutable, it might seem like we're making the local parameter exactly the same as the calling parameter. But that's not really the case. Instead, we really need to understand what's going on in memory for all of this data. Let me show you a slight variation on what we just saw. We're going to change the function so that it assigns a new list to val1. It's not just adding something on, like in the previous case, it's actually assigning something different. What do you think will happen? Okay, let's see. Whoa, what on earth is happening? I thought we just learned that lists were mutable, and here I am trying to change something, and it does not actually change. I got the same list I started out with. The function didn't do anything. To understand this, we need to understand that a mutable data type is really a reference to data values. That reference, which is called a pointer in some other languages, is what's really being copied. When you have one of these mutable data types, this reference is automatically dereferenced when you're dealing with the type. So it seems as though you're just dealing with the data that it refers to. Let's look at a list, which can help everything make more sense. Let's say that we have a list named list1, and it's got a couple of elements in it. The actual variable, list1, that is, the box in memory that is named list1, does not actually have all the elements of the list in it. Instead, the box holds where the list is going to start in memory. It says, here's where the list of stuff will be. The actual elements of the list will be in a different part of memory. And the box, the variable itself, is just saying where this stuff will be held. Now, if we come along and we create a new variable, list2, and we set it equal to list1, what it does is get a copy of what's in list1's box. But what's in that box is just the info saying, this is where our list is. It starts here. So, list2 is going to be pointing to the same list as list1 is. It's not just a copy of the list elements, it's the exact same elements. Notice what happens now if I make a change to list2 by appending on one more item. It's going to actually change the list itself. We didn't create a brand new list, we just added on to the existing list. So, since both list1 and list2 are using that exact same list, this changes both lists. If we were to print out list1 at this point, we'd see the values 3, 5, 7. Now, what if we did something different, like assigned a whole new list to list2, like you see here? Notice now that we're not just changing the list. We're not taking what's already there and making a change. Instead, we're assigning a whole new value to list2. So, that's changing what's in the actual box belonging to list2. List2 is now going to have a whole new value. It has a totally different list that it points to. If we print out list1 at this point, it's going to be the same as before. List1 didn't change when we assigned a new value to list2. So, turning back to our parameter passing, let's review why even these mutable things are not really any different than the immutable ones. If we look back at our previous example, when we call the function, we copy the reference to the lists into the equivalent area in the function activation record. But they're still referring to the same actual list of elements as in the calling parameters. So, when we make a change, like adding val2 onto val1, we get a change that not only affects val1 in the function, but also affects the list as seen by the calling side. After the function finishes, those changes it's made will persist. On the other hand, if we go back to our other example, where we set val1 to a new list, we get different behavior. We start out the same way when we call the function and the parameters are passed in. When we assign a new list to val1, we actually end up with a new list created, with no change to the old one. So, when we leave the routine and print out the calling variable, we see that it was unchanged by the function. I realize that this can be a lot to absorb at once, but once you understand exactly why certain things are mutable and others are immutable, it'll be easy to identify them as mutable or immutable, and to understand exactly how they'll be affected by a function. It'll make sense why we say that we're always passing by value into a function. We're always making a copy of the value. It's just that sometimes that copy of a value is just a reference to something else in memory. And we can still change that other thing that we're referring to. Let's look quickly at one more example to make sure that we've got this down. What would be output from the following code? Well, list A gets changed by the function, since the function modifies what was in the list. List B is not changed by the function, since the function tries to assign a completely new value to it. Whenever we see data types that are mutable, it'll help to remember that they're behaving like this underneath. Alright, we've spent a lot of time in this lecture talking about parameter passing and how all of that is done. Since parameter passing is central to how functions are used, it's critical to understand how this parameter passing is done. There's one more aspect of parameter passing that I want to discuss though, and that's default parameters. We don't always have to specify each of our parameters. Basically, in the parameter list, we give a default value for the parameter that can be used if the caller doesn't specify it. Let's consider a function to calculate miles a car travels given a number of gallons of gas and the miles per gallon it gets. Notice that for MPG, we are setting a default value. We follow the parameter name with an equal sign, and then the value that the parameter should take if it's not specified. This gives us a couple of different ways to call the function. First, we can call it just like always, where we specify both parameters. In this case, we have 10 gallons and are getting 15 miles per gallon, so we have 150 miles. There's no difference in the way the call in that function works in that case, and it didn't matter that we had the default value. However, we also have the option to leave off the parameter that has a default value. In the case you see here, we specify just one parameter, which will be the first one, gallons. The other parameter, MPG, is determined from the default value, which in this case is 20. So we get 200 miles total. We can extend this to any number of parameters with default values. Here's a madlibs function with 4 parameters, all with default values. We specify an animal, adjective, city, and food, and we get back some crazy sentence incorporating all of them. We could call this function with any number of parameters, from 0 to 4. Notice that if we specify one parameter, it's always the leftmost, or animal in this case. If we specify 2 parameters, it's always the 2 leftmost, or animal and adjective, in this case, and so forth. So, when you're specifying parameters, you have to realize that they're getting mapped in order from left to right. But suppose you want to specify some parameter that's not the leftmost one. Well, you can specify the parameter you want in the calling function. Let's look back at our madlib function again. For example, here we set the value of food to be pizza. The other variables, animal, adjective, and city, will all still get their default values. When you're specifying parameters by listing the specific local parameter and an equal sign, like in this example, it's called a keyword argument. For this kind of parameter, you specify by position first, and then give any keyword arguments after that. So, for this example, we're specifying animal by listing it first, without giving the keyword. It's the leftmost argument, so it will get mapped to the first argument, animal. Then we specify food and city using keyword arguments. Adjective gets its value from the default. So in the end, in this case, the parameter values are cat for animal, green for adjective, Denver for city, and steak for food. So this example shows a little of everything. We have a parameter value set by position, that's animal. We have parameters specified by keyword, that's food and city. And we have a parameter value set by default, that's adjective. As a word of warning, default values can get tricky if you use them for mutable data, or define them to equal a variable. I'd recommend that you only use default values if the default will be a fixed immutable value. We've seen here that there are a variety of ways to handle data in functions, from global variables to mutable and immutable parameters to default parameters. Understanding this will be helpful as functions take on an increasingly large part of our programming repertoire. My key piece of practical advice is that you should try to keep things as simple as you can to still do what you need to. So, when you write a function and think you need lots of parameters with default values or mutable data, and are using values from outside the function so that scope is a big issue, first stop and ask yourself, is this really necessary? Often you'll be able to come up with some other options that are much simpler and easier to use. Alright, at this point, you've really crossed a threshold, and you can be excited about how far you've already come. You've now seen all the fundamental components of programming that people have used for decades, and that still form the core of most of the software all around us. So, in the next lecture, we're going to look at how to take a more systematic approach to debugging our programs.